So our next talk is going to be delivered by Professor Ekene Okafor from Kyushu University. So please start.
Thank you very much. Thank you for the introduction. And thank you, the organizers of this workshop, for this opportunity to present this topic, liquid ammonia spray combustion in swirl combustors. I was told to do a review on subjects or papers related to this topic, but it's a relatively new topic in ammonia combustion, liquid ammonia spray combustion. So we don't have a lot of data on this yet, just a few studies here and there. And I'm going to be doing a review of those works that will help us to understand the challenges of flame stabilization and emission control in this area of study. I'm presently working full-time at Kyushu University, but I'm also at the same time working as a visiting researcher at the National Institute of Advanced Industrial Science and Technology, AIST. The work I'll be presenting is mainly the focus of my research at AIST. At AIST, we're looking at the development of liquid ammonia spray combustion systems for next generation gas turbines. And the work we're doing there at AIST is actually in collaboration with Tohoku University and IHI Corporation. So I'd like to start by acknowledging the invaluable contributions of members of Professor Kobayashi and Hayakawa's laboratory, this work. And also I want to acknowledge the contributions of our partners at AIST, at IHI Corporation, and also my colleagues at AIST. This is an ongoing collaboration funded by NADO. So this is the scope of my presentation, the talk I'll be giving. So let's go back here. Okay. Yeah, I want to talk about liquid ammonia spray combustion, why we are doing liquid ammonia spray combustion, why this is important. And then I'll look at the challenges of liquid ammonia spray combustion, which is actually just related to the spray characteristics and of course, NOx emission. When I talk about NOx formation, I'm really referring mainly to N2 emission. It's quite a big problem when it comes to liquid ammonia spray combustion. And then I'll discuss some of the experiments we've done so far in the laboratory and also in the field in gas turbine test facilities. Then we'll look at possible areas of future collaborations and some perspectives. Okay, so at AIST, in collaboration with these other organizations, we are trying to develop these combustor systems for liquid ammonia. And the reason is because from our experience, it's more desirable to burn ammonia as a liquid spray than as a gas. Because in large scale facilities that are burning ammonia, you have, like in the facility that we have at AIST, is a 50 kilowatt gas turbine test facility. And ammonia is usually stored as a liquid in such facilities. See that? This one, right? Yeah, ammonia is usually stored as a liquid in such facilities. So for us to get ammonia into the combustor as a gas, we have to first of all vaporize it, and in our case, we compress. Okay, these equipment, the vaporizer, they're quite expensive, and also they are space consuming. And when the scale of the gas turbine increases, the performance of these equipment, the performance and also the size increases, and that means cost increases. At IHI, they are doing experiments using a 2 megawatt gas turbine. And in their case, they require a large scale vaporizer, high performance vaporizer, and also an accumulator for the gas. Because when you vaporize, you have to accumulate a large amount of gas to ensure very steady supply of the gas. So these equipment, because they're quite costly, our aim is to do away with this equipment. We can reduce the cost of ammonia gas turbines by just sending liquid ammonia directly into the combustor in this form. Okay, we can do that. And again, when you consider gaseous ammonia combustion in these facilities, there's a time lag between when you get the liquid from the storage till when you get the gas into the combustor. This time lag actually would make gas turbines filled with gaseous ammonia. It would make them difficult to follow load fluctuations. Okay, so whenever you have a load fluctuation in such systems, Due to this time lag, you have problem. They'll have problem following the following the load response, having a good load response. So that's also one of our objectives, to improve the load response of ammonia gas turbine by using sending liquid ammonia directly to the combustor. And of course, you know, liquids have a higher volumetric energy density than gases. So in larger scale gas turbines, you prefer to have your supply the fuel in liquid form. But the problem is that liquid ammonia spray is more difficult to burn than gaseous ammonia. We already know that gaseous ammonia has its own difficulties, the low burning velocity, which makes it difficult to stabilize the flame. But liquid spray introduces an extra layer of difficulty into ammonia combustion. So I'm going to be talking about that in the next slides, but the difficulty is actually the reason why we're still working. It's good. The challenges of liquid ammonia spray combustion is related to the properties of liquid ammonia. So I want to talk about these properties. Here I've compared the properties of 4 different liquids: ammonia, ethanol, water, and diesel. This is actually a graph I just copied from Fan et al.'s article. And the properties I want to draw your attention to are these 2 properties: the boiling point and the latent heat. Okay, you can see that the boiling point of ammonia at 1 atm is quite low. It's negative 33 degrees centigrade. If you look at the saturation pressure, it's quite high. The saturation pressure at room temperature is about 9.5 bar, sorry, 8.5 bar, around 9 bar. And that's pretty very high. And the implication of this is that when you want to supply liquid ammonia in your system, one of the challenges you might be having is the high tendency of vaporization along the supply line. Because if you have any little decompression along the supply line, you're going to have a two-phase flow going on. One of the problems with this is that you find it difficult accurately measuring flow rates. But more importantly, when you have this kind of gas pockets in the liquid, when you inject, when you're at injection stage, when you inject gas pocket, a liquid with gas pockets, you're going to have an unstable spray. The spray is going to be unstable. And knowing that ammonia has a low combustion intensity, when you have this kind of instability in the spray, it's going to affect flame stabilization. You're going to have problems with flame stabilization. So this is one problem you don't want to have in your liquid ammonia combustion systems. Okay, but there's high tendency of having this, so you have to design against it. And then again, one other issue is the tendency of flash boiling. I called it an issue or a problem because flash boiling is beneficial. We want to have flash boiling in ammonia combustion. But again, it can be a problem if we don't control it very well. So actually, I'm going to talk about that later. So flash boiling is something we have to understand, predict, and be able to control in order to have very good combustion of liquid ammonia. Then the large latent heat of liquid ammonia, the challenges associated with that. This is actually one of the biggest challenge of liquid ammonia combustion. The main problem with liquid ammonia is because it has this very high latent heat. And the implication is that you have this significant evaporative heat loss or evaporative heat cooling effect of the spray. Okay, I want to talk about this also in the next slide and see how this can affect flame stability and also emissions from these flames. Looking at flash boiling, the flash boiling phenomena happens when you have a liquid. Let's say you have a liquid with a saturation pressure Psat here, and you inject this liquid, let's say from this point, into an environment, let's say a combustor at a pressure that is below the saturation pressure of this liquid. What you get is that this liquid becomes suddenly superheated, gets into a metastable state, and it breaks up violently into small droplets. This is very good. It's good because we want fast atomization, we want high evaporation rates, and that's what flash boiling gives us. Okay, in ammonia combustion, because ammonia has a relatively Psat, it has a very high tendency of flash boiling. The degree of superheat is what we can use to measure the tendency or the propensity of flash boiling, and it can be measured as a change in temperature, change in the difference between the injection temperature and the temperature of the environment. Sorry, the saturation temperature of the liquid and the injection pressure. Okay, it can also be measured as a ratio of the saturation pressure of the liquid at the injection condition over the ambient pressure. Okay, so when these guys increase, it means you're going to have the high tendency of flash boiling. So, as I said, flash boiling is good, you want it, but at some conditions, it can actually hinder spray dispersion. Okay, it can actually lead to low poor mixing of the spray and air. At Tohoku University, Professor Kobayashi's group looked at the spray of liquid ammonia, flashing spray of liquid ammonia from a hollow cone injector. When you inject a liquid that is not flashing, like let's say you inject water at room temperature through a hollow cone injector, what you're going to see a conical shaped spray, and the inner part of the spray will be hollow. That's why it's called hollow cone injectors. But in the experiment, like this data from their study, when they injected flashing ammonia spray through this kind of injector, the inner part of the cone wasn't hollow. Actually, they got a lot of you can see this central axis of the injector had a lot of droplets kind of aggregating at the central axis of the injector. So it's something that looks like a collapse of the spray towards the middle of the injector, and this is because the spray is flashing. This is what we don't want to have, because it's not allowing very good dispersion of the spray. And they did some measurements. I believe the data should be published sometime soon. It's under review. They measured the droplets diameter across this spray, and they found out that towards the central axis of the spray, the droplet diameter increases. So this is like when these droplets aggregate at the middle of the spray, they coalesce, so their diameters increase. That's also one thing we don't want to have. And the numerical simulation, they did earlier analysis of ammonia spray, non-reacting spray, and they were able to capture this kind of coalescence of, let me call it collapsing of the spray. You can see from here, you see when the liquid was injected, you see something like that looks like a hollow cone at the beginning, and gradually after that, you see a collapsing of the spray towards the central axis of the injection spray. Now, other studies, actually, our group at AIST also have seen similar behavior of flashing ammonia spray. Fan et al. Looked at two different conditions of the liquid ammonia. They looked at this condition, which has a very large degree of superheat. And also this other condition 2, was achieved by cooling the liquid before injection. Okay? The liquid was cooled to temperatures around -20 degrees. And this is their findings. For case 1, this case, which has a high degree of superheat, you see that the liquid is collapsed. The spray is collapsed. It's flashing. The droplets are quite small, good atomization, probably fast vaporization, but it's collapsed. It's not very good for mixing. But in the case 2, where the liquid is partially flashing, almost not flashing, you see a very nice dispersion of the spray. But one problem with this condition is that if you look very closely, you see very relatively large droplets here. Again, this is what you don't want to have in your liquid ammonia spray combustion. You actually want to have good atomization through flashing, but you don't want it to collapse. A similar behavior has been found by Professor Roussel's group in University of Orleans, France. Pelle et al. looked at injection of liquid ammonia using a GDI injector. They were studying combustion in engines, ammonia combustion in engines. So they looked at this liquid ammonia flashing spray. They compared the properties with that of ethanol and gasoline. And notice that for the flashing ammonia spray, the spray also collapsed. If you compare this to that of gasoline. And also quite importantly, they noticed that the flashing ammonia spray had a longer penetration distance. You can see it's longer than that of gasoline. Okay, so and also in their study they noticed that ammonia spray seems to be more sensitive to the conditions of the liquid before it's injected compared to gasoline or ethanol. This has a very interesting implications in application because gas turbines that are located in regions where you have daily temperatures varying widely between seasons, you're going to have difference in spray structures. That what means. Okay, so in AIST, this is liquid ammonia injection conditions at FRIA AIST. The experiment we did at AIST, we did studies that spanned the whole length of the year from one winter to the next winter, and we're measuring injection conditions and also looking at emissions from the flame. And this was the result we got from those measurements, that in winter, we could see that our injection conditions were very close to, the temperature was close to zero, because there at where the gas turbine is or the facility is, the daily temperatures can vary from zero until about 35 degrees, zero in winter and about 35 degrees in summer, quite a large variation. So, and that affected our injection conditions. And one interesting thing we noticed, actually without really thinking about spray patterns, was that in winter, we used a particular injector for our experiments in winter, and we're able to get very stable combustion of pure liquid ammonia in the 50 kilowatt gas test facility. And then we used the same injector in summer, and we couldn't replicate that condition. We couldn't stabilize pure liquid ammonia. Then we weren't thinking about the spray pattern, how the seasons or the injection conditions could affect spray patterns. But we can understand that the condition of the injection, the injected liquid, can have a very important effect on the spray pattern and also flame stability as well as emissions. Okay. Then this study recently, actually earlier this week, this study was released earlier this week. This is from Professor Kobayashi's group again. They were looking at the effect of the degree of superheat, as well as the effect of aspect ratio of the injector on the structure of ammonia sprays. The aspect ratio here means the ratio between the length of the injection hole and the diameter of the injection hole. This is a single hole injector they used in this study. What they noticed was that for very small aspect ratios, you see this kind of spray pattern. This is this column spray coming out from the injector. But as you increase the aspect ratio, you start seeing some flashing. For this condition, you only have mechanical breakup of the liquid. And at larger injection aspect ratios, you see very completely flashing, widely spreading spray. Okay, so aspect ratio has very interesting effect on the spray pattern. And again, they also looked at, this is the effect of, between this and this, have the effect of degree of superheat. Here, the degree of superheat is 50 Kelvin. Here, it's 35 Kelvin. And you can see if you compare this and this, you can see some droplets in this spray. This is partially flashing spray. It's not fully flashing, so you still have some large droplets in the spray. Okay, now about the large latent heat of vaporization of liquid ammonia. As I said, it leads to a very significant evaporative cooling effect. We try to look at this by measuring, to understand it, we try to measure the temperature profile inside a combustor with non-reacting liquid ammonia spray. We injected a swirling preheated air. Temperature of air was at 230 Kelvin. And then we injected liquid ammonia, and then we measured the temperature along this line. Along the central axis. And what we saw was that just above the injector, the temperature was about -50 degrees centigrade. There was a lot of cooling going on there. So what it means is that if you're going to have a flame inside this combustor, there'll be a lot of heat extraction from the flame for evaporization of the liquid, of the droplets. And so this is typically what you're going to find out, what you're going to see. So this is liquid ammonia stabilized with an axial swirl combustor. The inlet temperature of air was 230 degrees centigrade, but you can see at the base of the flame is lifted, because at the base of the flame, the temperature is quite low, so it's difficult for the flame to get attached to the burner. Okay, so this tells you that it's need for you to like compensate for this high latent heat when you're trying to stabilize liquid ammonia sprays. And also it's important to have very strong recirculation in this burner, in liquid ammonia spray combustors, to have like heat recirculation from downstream to upstream of the combustor. Then one other interesting aspect or effects of this evaporative cooling that was captured by Professor Im's group, it was in their DNS analysis of liquid ammonia droplets evaporation. They injected subcooled droplets inside into environment with different temperatures. Okay, then temperatures varied from 220 Kelvin till 600 Kelvin, and they were looking at how these subcooled droplets would evaporate. These are subcooled, so there's no it's not flashing. The droplets were not flashing. And some of the interesting result they obtained was that one is that evaporative cooling effect may encourage longer droplet lifetime, especially when you have clusters of droplets in the spray. So it means that when you have flash boiling and the spray collapses, you might end up having longer penetration length. That's what Professor Russell found in their studies. That could explain that. So these clusters of droplets, they seem to like help each other to live longer. That sounds a little bit human to me. Okay, so what it means is that you really want to have very good dispersion of these droplets in liquid ammonia spray combustion. And again, they noticed that the evaporative cooling effect inhibited boiling of the droplets, even at very high temperatures, even at temperatures as high as 600 degrees centigrade, 600 Kelvin, which is like 2 times more than the boiling temperature of the droplets. So the droplets did not burn in the flame. So an implication of that, okay, this is the study from Kyushu University. Once again, I just want to show that this one is a less flashing spray where you have very large droplets in the spray. These droplets actually, I was told that these droplets lived longer, lived up to about 1 meter above the injector. So they didn't actually vaporize. They didn't vaporize easily. So when you have large droplets in ammonia spray, you might find it difficult having fast vaporization because they don't easily boil. Okay, and in some of our studies at Kyushu University, we had a condition where there was we had a condition where there was a mixture of I don't want to have this. Okay, so we had a condition where we had injection of supercooled droplets. Okay, yeah, we had supercooled droplets injected at the same time with a flashing of liquid ammonia spray. All we can see there is that the supercooled droplets could not vaporize inside. There was a rain of liquid ammonia spray jumping out of the combustor. So these droplets did not vaporize inside the flame. They did not vaporize, okay? So in liquid ammonia spray combustion, it's like you don't want to have large droplets or supercooled droplets in your spray. So we really need flash boiling, very good atomization, fast evaporation, but still we don't want this flashing spray to collapse. So these are the problems that we need to solve in liquid ammonia spray combustion. And then the cooling effect, this evaporative cooling effect will affect N2O emission particularly. Of course, it's going to affect all the emissions, NO emission, but I want to talk about N2O emissions here. Previously, in our studies on gaseous ammonia combustion, we tried to look at the effect of heat loss from ammonia flames on emissions. We looked at, we used different combustor liners, some that were uninsulated to allow high convective heat transfer, and some of the liners were insulated to prevent heat transfer. And what we noticed was that with an increase in heat loss from the flame, we got an increase in N2O emission, okay, as shown here. And then we tried to see if we can control these emissions using two-stage Richling combustion. So we developed a simple two-stage Richling combustor like this. And then, first of all, we started by using a combustor that was not insulated. So this time around, we still have large heat loss from the flame. And this was what we got, this red plots here. So with large heat loss, we were able to get this kind of, then the next thing we did was we insulated this combustor to reduce heat loss from the combustor. And then we got these green plots. So there was a reduction in N2 emission, and that's good. Then the next thing we did was we decided to uninsulate again. We just removed all the insulations and allowed convective heat loss to have its way. But this time we decided to increase this HP. We decided to increase this HP, which is the length of the primary combustion zone. And when we did that, we got these blue plots. So we had better control of N2O with longer combustor, even though there was some heat loss from the flame. Hayakawa et al. Also did some quite interesting studies on, quite interesting measurements on N2O emissions from stabilized, wall-stabilized flames. It's a stagnation flame experiment. And also they looked at in details into the chemistry of N2O production and control. This is one of their simulated data. I just want to use it to explain why we could have N2O control by just increasing the length of the combustor. When you look at the post-flame, this is post-flame data of an adiabatic flame and the stagnation flame. For the stagnation flame, the stagnation wall has a temperature of about 500 Kelvin, so it has low temperature. So there's heat loss towards this wall, okay? And what you see is that for the adiabatic flame, the N2O emission or the N2O mole fraction decreases continuously in the post-flame. But for the flame, for the stagnation flame, which has heat loss, okay, these are the temperature profiles actually, okay, for the stagnation flame, because you have heat loss and you have the N2O profile kind of gets to equilibrium at a point, okay. This is it doesn't decrease further. And the reason why you have this behavior is that ammonia is N2O is mainly produced in the flame through this reaction number 4 to 3. And then it's consumed mainly through these reactions, this reaction R46, R47, this duplicate reaction, that's why I labeled it that way. And then, and also this dissociation reaction. This is the rate of these reactions. You can see that the production of N2O and also its consumption through these reactions are only very active inside the reaction zone. Okay, they're quite active inside the flame, But in the post-flame, you have this dissociation reaction playing an important role in the post-flame. So when you have a longer residence time in the combustor, you allow a long post-flame region. You're going to allow enough time for this N2O to dissociate through this reaction number 49. That could be the reason why we could have better lower N2O emissions with longer combustors. This could be applied to liquid ammonia spray combustion. So with that, we did some experiment at Kyushu University, starting with, we started our studies trying to develop these liquid ammonia spray combustion systems by looking at very fundamental aspect of liquid ammonia spray combustion. And this was the experimental setup. One of the things I want to point out here was that we tried to ensure that we didn't have gas pockets inside the supply line by cooling the supply line right from the supply from the liquid ammonia, this is a liquid ammonia cylinder, up to the combustor. Okay, we cooled it. And then we try to see, we try to control these conditions so that we don't have very varying spray characteristics in our study. We're not interested in studying the spray characteristics in this study. We're just looking at stable combustion and then measure the emissions from this combustion, from these stable flames. And you can see these conditions are actually flashing spray conditions. And then we started this study actually with axial swirl combustors. But we noticed that with axial swirl combustor, the recirculation zone is not that strong. The combustor had a recirculation zone that was not that strong to help us to have a very good heat recirculation. So we redesigned the combustor to a tangential swirl combustor, and we measured the flow field in the combustor and found that there was no outer recirculation zone, but the inner recirculation zone was very large and there was a very strong reverse flow, which we believe is quite important in liquid ammonia spray combustion to enable heat recirculation and as well as help mixing with air. Okay. So then the result of this study, we were able to get very the combustor inlet temperature was 500 degrees centigrade. This was 500 degree Kelvin, which was very important to compensate for the latent heat of vaporization of liquid ammonia, the high latent heat. And we started by co-combustion with methane. Okay, and this is liquid ammonia co-combustion with methane. Ammonia heat fraction in the mixture was 70%, 80%, and 90%. And you can see we got stable combustion over a relatively wide range of equivalence ratios. These are the flame structures, flame images. These points are the same as these points on this graph. And then we looked at emissions from these flames, and we can see that N2 emission was quite low. It's lean and rich conditions because we were able to enhance the flame and enhance the combustion of liquid ammonia by combustion with methane. This study was further extended by Yamashita et al. They looked at pure combustion of liquid ammonia alone without any additives. And what they did was that they increased the CIT from here was 500 Kelvin with a little bit, with 100 Kelvin increase in CIT. They were able to get stable combustion of pure liquid ammonia over a range of conditions. And what you can see here, they noticed that with an increase in CIT, you have an increase in NO emission that's expected. And also you also have a decrease in N2O emission with an increase in temperature of the combustion air. Then using that model of the combustor, a tangential swirl combustor, we developed a two-stage Richling combustor for the 50 kilowatt gas turbine test facility at AIST. The important point about this combustor was it was a two-stage combustor. The height was identical with the gaseous ammonia combustor we used in this facility before. We couldn't increase the height of the combustor during those experiments because we were limited with by the design of this facility. Okay, so and also the combustor was it was fume cooled. It had fume cooling holes for cooling the walls of the liner, which is a normal practice in gas turbine combustor design. So this was the combustor we started this study with, this combustor. And what we noticed was that when we did measurements of, we studied stability of the flame using this combustor, we noticed that the stability of the flame was dependent on the temperature of the combustor liner. So there was a temperature below which we couldn't get stable combustion of the flame. Okay, so and this temperature, this limiting temperature increased with an increase in ammonia content in the flame. So, but the problem was that this combustor, because it was well cooled, the temperature, we couldn't get the temperature above 600 degrees centigrade. So we decided to redesign the combustor. This time around, we developed a combustor without wall fume cooling, this other combustor, and with this, we had very high wall temperatures, and we were able to stabilize pure liquid ammonia over a range of equivalence ratios. But there was a problem. Here comes the problem, N2O emission. So this is the new combustor. We're able to get pure liquid ammonia combustion and also 50% liquid ammonia with methane. But when we looked at N2O emission, we found very large N2O emission from the flame. Okay, and then for this condition, this is the temperatures of the combustor walls. We measured temperatures along the walls of the liner at different points. What we noticed was that for this condition where we have pure liquid ammonia combustion, as the flow rate of liquid ammonia increased, the wall temperature became a lot non-uniform. It became quite non-uniform, and that points to probably the spray pattern. Okay, it seems like we didn't have an even spray pattern, and also maybe there was large penetration of longer penetration of the spray. Maybe the spray was also wetting the walls of the combustor. So, but we couldn't look at what was going on inside the flame. So we're looking at just temperature measurements and emission measurements. So we're a little bit limited in these studies then, but this was a big problem that we are still trying to solve. Okay. So now, during that study also, AIHI was also looking at liquid ammonia combustion in 2 megawatt test facility. And in their study, this is the study they did with the previous, the original combustor. And they noticed that NOx emission from liquid ammonia combustion was higher than that from gaseous ammonia combustion. This is measurements from the combustor, from the exit of the combustor. And then when they're using that old combustor, they tried to get, they measured N2O emission also, and you can see that from the measurements, when ammonia heat fraction exceeded about 70%, there was a very rapid increase in N2O emission, okay, for that old combustor. But in more recent development at IHI, they developed a new combustor, and this new combustor now actually can efficiently burn pure liquid ammonia, 100% liquid ammonia, and also have 0 N2O emission. You can see from here. So this is this graph shows the greenhouse reduction rate for the old combustor. The greenhouse reduction rate. Okay, for this this is what you see here is co-combustion of liquid ammonia and natural gas. Okay, so this greenhouse gas reduction rate means the rate of reduction of CO2 as well as N2O. So at very high concentration of liquid ammonia, you start having N2O emission. That's why the greenhouse reduction rate kind of decreases. Okay, but with their new combustor, they were able to get very complete oxidation reduction of N2O in the combustor. Okay. So with that, I would like to summarize, and I can say that liquid ammonia spray combustion is very important in large-scale combustion systems. And the spray characteristics significantly affects flame stability and emission. And we can say successfully we've studied liquid ammonia spray combustion in laboratory scale and large scale facilities, but this is the starting point. We've actually noticed that there are a lot of challenges and things that we don't quite understand. So it's just a study that tells us we can actually do this, but there's work to be done. So for future focus, it's important to have more fundamental measurements in liquid ammonia spray combustion, non-flashing, it's important to look at spray characteristics in non-reacting and reacting conditions, okay? It's important to predict flash boiling conditions because we can see that flash boiling actually has a very important effect on flame stability and also will affect emissions. Also, we need to understand flashing and non-flashing droplets. Droplets combustion, single droplet combustion, group droplet combustion is quite important. We need to understand the behaviors of these droplets. And also, it's quite important to look at optical diagnostics in liquid ammonia spray flames. This is something we've not been able to do. And previous presentation talked about looking at an N2O profile in the flame. This is something also very, very important in liquid ammonia spray combustion. But what I know is N2O optical diagnostics is still, I don't know whether we can do it, but it's an area that we need to put our efforts towards. And also we need to understand how two-stage, how NO, N2O, and all this are produced in two-stage combustors, because there's need for us to actually modify these combustion in emission control strategies. Also, we should look at enhancement of the flame for that, and one option we can look at is plasma-assisted combustion of liquid ammonia sprays. So with this, I want to end my presentation, and let's discuss.
Fantastic. Thank you very much. The talk's open for discussion and questions.
Hi, Dr. Okafor. Thank you for the presentation. My name is Marina from Kyushu University. So my question is in regarding to N2O in liquid ammonia. So if I've understood correctly, your point is that N2O can be partially dependent on ensuring that there's a sufficient high temperature region for reduction. But you mentioned that with liquid ammonia, it's more difficult to ensure that there is this high temperature region, or there might be cold regions on the walls. So if it's not confidential, can you comment on some design changes that can be made to ensure that N2O can be reduced in liquid ammonia?
Thank you very much for that interesting question. Actually, the problem we think we have in our previous studies was that we had when the spray pattern is not quite even, it's not even. You have uneven spray pattern, you have droplets group combustion. So in this case, you're going to have local regions in the combustor where you have very low temperatures, okay? And of course, these regions of low temperatures, you could have quenching at those regions. And when you have quenching, you have unburnt ammonia, you're going to have N2O being produced from those regions. So one of the things we're looking at is we are trying to develop injectors that are really very good, as in that will enhance spray dispersion and mixing in the combustion. Okay, so we have to find a way to avoid any instance of group droplet combustion in liquid ammonia spray combustion, because we have to. That's the way to avoid low temperature regions that could lead to high N2O emissions. Okay. So for the measurements we've done so far, we don't really, because we don't have any optical access into the flame, we don't really know how these N2O were produced. So we're still looking at it just like conjecture. Like this is where we should focus our attention. Okay. I don't know whether that answers your question. Okay, thanks.
Further questions? Bassam.
Thank you for the talk. Interesting findings, but I couldn't but think that many of this could have been predicted using CFD. It appears to me, and correct me, this is not a criticism, but an observation, as a lot of trial and error, rather than, we could predict the flow patterns. We know what temperatures these droplets are likely to experience. Maybe our flashing evaporation models are not super accurate, but will give you some indication of trends. And I know that IHI have 200 ppm and you're measuring thousands. In other words, there's some knowledge out there that we could utilize and we could get us there faster. So I want your comment on the future direction by which, yes, you can't measure inside the combustor, but you could do all with CFD to help you design one that would avoid all things that you already found.
Thank you very much. That's a very interesting question. Actually, there should be a lot of work on CFD simulations, and as you say, there are a lot of models on for predicting flashing sprays for now. But the recent studies from Professor Kobayashi's laboratory shows that some of these models, most of these models don't actually perfectly well predict flashing conditions in liquid ammonia spray combustion. Okay, so there's this need for us to modify these models to validate them for liquid ammonia spray combustion. It seems like there's a different thing that's going on that we don't quite understand yet. Okay, so modeling this, the best way to go, of course, is to for us to get very good information about this combustion is to go by modeling them. But we also need experimental value data to validate these models that we need to use for the studies. I don't know if that answers your question.
Yeah, but currently it seems to be in cause and effect. We did these conditions, this is what the exhaust looks like. I think maybe you're right that we have to look inside to be able to understand what's happening. Otherwise, this iteration may take much longer. I had another question. How do you get 700 degrees air coming in?
700 degrees?
Yeah, sorry, yes, you have 700 Kelvin experiments, yeah.
Okay, we use, for the experiments in the labs, we use...
No, I mean in a practical system.
In practical systems, we're using a recuperator. The heat from the exhaust gases are just recuperated for heating the incoming air.
So what I'm trying to say is maybe EGR in here would be a better way.
EGR? Okay, what we're talking about now is a gas turbine combustion. EGR, we're not looking at EGR. What we do is actually this question opens a very interesting area of research that I didn't mention. You know, starting of these gas turbines is actually still a very important problem, because in the starting of these gas turbines we use methane for now. We burn methane, we start a gas turbine, and we don't actually start a liquid ammonia combustion until we've raised the temperature of the CIT to a particular temperature, actually above 400 degrees centigrade, before we can inject liquid ammonia. So this is actually a problem in liquid ammonia spray combustion. So what we do is, the way we raise the temperature is from we extract heat from the burnt mixture, from the burnt gases, okay? And so for us to get burnt gases, we have to burn something. So that's why we don't really start injecting liquid ammonia directly. We've not actually thought about EGR in these systems.
There's some designs which could do it.
Okay. Thanks.
Kitana.
Agustin has a question. So Agustin, go ahead.
Yeah, thank you. Hi, Ekene. Very good presentation, really nice work. The question is related to the nozzle size. So are you, from what I understanding from all the work that you're doing, you're assessing, again, a particular nozzle, but have you tried different geometries? And this goes to probably a second question of looking at these multi-phase stages that you're seeing when flashing some of the ammonia. Is that something that you're evaluating for the production of a very particular size of droplets, or is it just again now at the stage of seeing first how they behave with a particular nozzle, and then after that trying to then improve the combustor in itself, not the nozzle?
Okay, yeah, thank you very much, Augustine, for that question. In the beginning of this collaboration, we were not really interested in, we didn't look at the spray patterns from different nozzles. We're only interested in trying to stabilize liquid ammonia, measure emissions from there. But when we found out that actually the spray pattern affects all the things we're doing, now we are actually looking at different nozzles, different nozzle designs, as you saw in the data from Kyushu University. They are looking at aspect ratios. Also in the gas turbines, we're also looking at different nozzle designs that could give us better spray characteristics. Okay, so we actually, yeah, we are looking at different designs of nozzles for very fundamental studies and also for studies in these large-scale facilities.
And then thinking about that, for example, the multi-phase, you say you're looking into having stable combustion. When it was multi-phase, what was your experience? How is the flame looking at? Because I'm thinking again, potentially, it could establish two flame fronts, one with gaseous at the beginning, then second, that is using some of that unborn ammonia already in still liquid form, to then even denox the chamber. But in terms of stability, how was it looking at?
For the measurements we've done so far, we've not really been able to probe the combustor, like get optical access into the combustor at AIST. So I can't really tell you how the flame structure looks like with for different spray patterns. So it's something that we're going to be looking at in future. We're actually looking at that presently. But at Kyushu University, what maybe something related to what you're asking about might be this. So here we have a flashing spray, and also we had a subcooled droplets in the combustor. So this could be something you're asking about. When you look at this, I think this flame is just stabilized by the flashing spray, while the subcooled droplets are not getting involved in the reactions.
And this is something that you'll evaluate as well as part of the different nozzles that you'll try, right?
Sorry?
This is something as well that you will evaluate. Well, the guys in Tohoku will evaluate with different nozzles.
Yes, probably.
Yeah, brilliant. Okay, thank you.
Assad.
Thank you. Maybe go back to that, the summer winter flash evaporation slide there. So you mentioned that in winter you were getting good flash boiling, and in summer it went bad, or I guess somewhere in between. What was the design, I guess, criterion that you had to sort of work with in order to change it to a good flashing condition? And specifically, my question is about, do you need a certain degree of superheat and a certain pressure ratio threshold, right, before which you allow a margin so that bubbles do not form inside your nozzle?
This is what what you just said is one of the ways to control flashing sprays. The conditions of injection conditions, but if you can control it perfectly well, you can determine which regimes of flashing you are in. In this study, we didn't actually look at the spray. We didn't know whether it was flashing or not. We're only looking at flame stability. Was the flame stable or not? So we had different injection conditions, and then we're now looking at how this difference in injection conditions affected flame stability. Okay, so we didn't know whether it was flashing or not. But of course, these conditions are conditions where it should be flashing. Okay, so yeah, so we didn't look at that then.
Good question.
Well,
Very nice talk. Actually, my question is more for Assad. Then, so the turbulent spray workshop, are you guys also looking at ammonia spray flames or not yet?
Not yet.
Not yet.
Not
Will
yet,
you do?
But the
It's in the plan.
Yeah, well, it's not yet, I guess, is the short answer. But that doesn't mean that we won't be looking at this in the future. I think
Because I mean, this is answering a comment. They needs more data. It needs more validation of the CFD. That would be an excellent platform to do that.
That's right.
I've got a question. The large 2 megawatt facility, are you able to at least comment on what the combustor pressure was operating there at?
The IHI facility,
Yeah.
the combustion pressure is about 1 megapascals.
Right.
Maybe another question. I think we're running out of time. The last, the modified combustor, when you brought the N2O down to 0 or close to it, what happened in between?
I can't really talk about that.
Okay.
Details of that study, I'm sorry.
All right. Secret.
Okay. Any further questions for discussion? No. Okay, that's fantastic. I think that's pretty good timing, and please join me once again on thanking the speaker. Hour and a half lunch.
So it's yeah. So you want to tell us?
The lunch box is in a multi-function room. So please move upstairs, and the room is on the left-hand side. And please enjoy it. Yeah, thank you.
And for the online attendees, we start again at 2 p.m. local time in Tainan.